Namaskaram. Welcome to another video of GPU programming with Mojo. Today we shall learn about the concept of single instruction multiple data. Until now we have assumed that there is one thread which can act on one data element and perform an operation. But what if I told you a thread is capable of executing its instruction on multiple data all at once? This is the concept of SIMT, or single instruction multiple data. We will see in today's video how we can learn to further optimize our kernels, our GPU programs, so as to take advantage of this SIMD, combine it with SIMT, which is single instructions multiple threads, and further make our programs and kernels more efficient. We'll start off with importing certain libraries. The setup for today's program would be a vector of size 64 elements, and we'll do a simple kernel which is vector addition. Vector A adds vector B to produce an output. We'll initialize the vector with some random values and try to write the kernel. You see that the SIMD width as an output of this block is 4. So every thread has access to a register to execute an operation. The register is of a certain width. In this case, for my laptop, it's about 128 bits. So if I have to execute an operation of float 32, which is 32 bits, I can pack 4 such elements and produce an output. So if you have 128 bits, you can put 32 into 4. Or you can put int 8, which is 8 bits, you can put 16 of them. So you can pack more elements if you have a lesser or a smaller data type. And if it's float 64, it will be just 2 elements that we can pack. But the truth is you can pack more than one, which is what the SIMD is all about. Take advantage of all the spaces available in the register that the thread has access to make your program even more parallel. So with that concept in mind, we'll write our first kernel, which is called element-wise add. So step 1 is we have to take advantage of SIMT, which is single instruction multiple threads. For that, we use a built-in function called element-wise. This element-wise will help us create threads. We provide with some standard parameters like SIMD width, what's the target, the context, and the size of our vector. We want it to execute a function. So spin up multiple threads and execute a function. Which function? Add function. And this add function is an inline function defined here. This inline function is a simple vector addition, but it's sort of broken down into 3 steps, which you're familiar with. So prior to this, we have said get the global index of the thread and add the A vector with B vector to produce the output vector. Conceptually, it's the same thing, but now we are sort of further dividing this into 3 steps where we say load this from global memory. Load is fetch it from global memory, perform the operation, and store it back to global memory. Here we are not explicitly saying it, but we are doing the same. We are getting it from global memory, executing it, and storing it back. Here we are explicitly saying load, operate, and store. By using load and store explicitly, we get an option of providing SIMD width as one of its compile time parameters, which in our case is 4. So essentially we are saying grab 4 elements from global memory, operate, and store the same 4 elements back to the global memory. So instantly you can see you get 4x the benefit by making your program slightly more larger and bigger, but at the expense of getting a much more benefit than you were used to. So this concept of using element-wise for spinning up multiple threads, using load and store, and using SIMD width now leverages both the SIMT model, which the GPU is famous for, and the SIMD model, which CPU is actually famous for, but we are leveraging the best of both worlds here in this program. So at this point, these are the nodes just explaining the same program implementation we went through. And this block of code produces the output. Now, in the prior video, when we explained when we were trying to optimize our matrix multiplication, we learned the concept of tiling. Essentially, we want to grab multiple elements all at once and see if we can benefit from it. We also sort of understood that when a tile API is used, or when we simulate a tile operation, the compiler gets a hint that you will be fetching more elements because it's in some sort of a loop, and hence it tries to put all of them in a cache. So in the prior example, there were 16 threads grabbing 4 elements, but all of them were going to global memory and fetching the data. Here, the compiler sort of understands that since you will be using tile, meaning you will be grabbing more elements, hence requiring fewer threads, but it will try to put those elements even without you asking for it and putting it in the cache. A good analogy would be, let's say you're in a restaurant and you ask for a fork. The waiter comes and gives you the fork. Then you ask for a spoon. He comes and gives you that. Then you ask for a spoon again. This time he comes with a plate full of all types of spoons and forks and all cutlery, anticipating what you might ask, hence avoiding a round trip. That's pretty much how cache works. So here, in the tiling strategy, you have fewer threads, hence reducing the efficiency, but there are other optimizations the compiler will make so as to give you the benefit. This tiling strategy might or might not be more efficient than the earlier one. Sometimes the 16 threads are more powerful and they'll do a job far easier than a 2 threads here, where the tile size is 32 in my case. So we have to benchmark both of these and figure out which one is applicable for the use case we are trying to solve. But the advantage of using a tile is it can be combined very efficiently with a built-in function called Vectorize. Now, before we see the implementation, let's see a visual of it so as to understand it better. So let's make this bigger. So the step 1 in our today video series that we saw was use SIMT, and the threads will grab 4 at once, 4 elements at once, and produce an output. And it looks something like this. 16 threads, 4 elements, 64 elements processed. When you use a tile, you're using only 2 threads, since the tile size that I've chosen is 32. But a single thread sort of loops 8 times, grabbing 4 elements at once and produce the output. Now, the concept of looping sort of makes us cringe because any looping makes the compiler and the program less efficient if it has to loop, especially in the GPU world. So one might ask, why can't we just spin up threads and be done with it? In some cases, the GPU won't allow you to create as many threads as you want. Let's say you have a billion elements. You cannot create a billion threads. So you'll have to remember how to work with fewer threads sometimes. That's where tile becomes very important. But more importantly, this tile API gives you the access to cache and other operations, which the compiler will help you optimize as much as possible. So it looks something like this, where it'll sort of loop, but only 2 threads are involved. But then there is another function called Vectorize, which will help you do this. It will take the looping of the thread, here in this case 8 times, to process 32 elements, which is the tile size. And instead of you looping 8 times, it will unroll the loop and help you execute all at once. So you can think of it as a burst mode, like this. And that's the advantage of combining the tile concept with the function called Vectorize. So a Vectorize is a function which will take all the iterations in a loop, arrange them as a straight line instructions for the hardware to execute. So it looks something like this. At a programmatical level, it looks something like this, where if you have a loop, it will load, add, store, load, add, store. That's the operation if it's a loop. Whereas an unrolled vector would arrange the hardware instructions at the assembly level as process, load 0 to 7, 8 to 15, 16 to 23, 24 to 31. The reason why it can do that is because it knows there are only 32 elements, and that's your tile size. It can fixate the start and end point automatically even before running the program. Once it knows where to start, where to end, how many elements to grab, where to fetch the cache, like it knows all the instructions beforehand, it can arrange in a very sequential manner on the register and then press the play button, which executes all of them instantly, as opposed to guessing each time how many times should I loop, how many times should I go and fetch. And that's the advantage of unrolling, which is knowing the size of the loop beforehand, hence arranging the instructions on the hardware, which gives you the speed of light. The program itself follows a similar pattern where we start off using element wise, which will give you SIMT, which is spin up multiple threads. But this time you're not doing element by element, you're going tile by tile. So you specify the tile size and tell the program how many tiles you have to navigate. Within the program or within the function, you have an inline function. And notice there are no loops in it. You simply say load, operate, store, but you capture all of them in a single line called vectorize. So essentially the vectorize is your sort of simulating this concept where if the vectorize wouldn't have been there, you would have written a for I equals tile size, you would have set the start size and then did the same thing, load, operate and store. But you have to write the for loop, you have to specify the global start very carefully, and then needless to say that you have to mention add parameter, which does the same unrolling as the vector does. But all of this 6 lines or 7 lines of code is eliminated by using a simple vectorize function. Needless to say that vectorize also gives you some other benefits. Since it's built in by the people who built the Mojo language, they would have sneaked in other compile time benefits that we are not aware of, but it will sort of handle the boundary conditions. Sometimes if the number of tiles is not equal to SIMD width, what do we do in those cases? So all those boundary checks and leaks will be avoided if you use a built-in function. So for 99% of your cases, you will benefit from using vectorize. And in some cases, you might want to use your own for loop for expert control. And this block of code produces the output for the vectorize function. So the journey that we have been through is we went from a scalar processing where one data element, one thread. We said one thread, multiple elements using the SIMD concept. Then we graduated from that to using tile. And from that point onwards, we said, why should we loop in a tile? Why can't we use vectorize and parallelize the elements in the tile to take advantage of not only the cache, but also the vectorize function, which will execute them in a straight line. So we are taking advantage of SIMT, which is built into GPU's execution model. We have taken advantage of SIMD, which is at the hardware register at the thread level. We've used tile, which uses the L1 cache and helps us with better fetch from global memory. On top of that, we have unrolled any loops that we can find to ensure that it executes at the assembly language level in a straight line and extracting every ounce of performance. Hope this helped shed some light into how we can further optimize. Hope you enjoyed the video. See you in the next one. Thank you.